Okay, you can continue your lecture now.
Yeah, okay. Thanks, Anupam Shripad, once more. And happy Independence Day to all. Happy Sunday, happy Independence Day. So, in this lecture, the keyword is going to be the chirality of word maps. I'll explain what this concept is. And it's a relatively new concept, and I think there are many problems, open problems around it. So, I'll explain all that. So, what is chirality in general? So chirality is kind of asymmetry of images of word maps. So in what sense? I'll explain that. And for this, there are two references. Uh, First one is this, both are recent references. So first one is this Gordeev, Kunyavsky, and Plotkin. And it's called Geometry of Word Equations. Over spatial fields. It's quite extensive survey. And this was originally written in Russian, but English version is available in so Russian research survey, Russian math surveys. Actually, this is a very nice survey overall for things related to word maps. The other one is more specific, and that is an article by Koke and Meng Che Ho. Uh, Ho. So that is also recent in communications 2018. And then there are many wide problems, and in fact, you can find lots of open problems in this. Okay, so I begin with this observation that if you take the two most famous word maps, so most famous ones are power map, so only one variable is needed, or you take other famous one, the commutator map. Uh, in either case, the image is closed under inversion. Inversion meaning G going to G inverse for every G. So that is a kind of symmetry. That's the symmetry which was being referred to in the very first line. So symmetry is with respect to inversion. So a closed under inversion is what is referring to symmetry in today's lecture. So this is a key thing, closed under inversion. And when such things do not happen, then you say there's some kind of chirality is happening, and you're interested in knowing how common or rare is this phenomena. And what the work of Koke and Milchu seems to be indicating is that the phenomenon is quite rare but not much is known about it. So we recall that word images were closed under taking automorphisms. And of course, the identity belongs to the images. But inversion is something which is not there in general. But if you observe lots of examples, you'll hardly find examples where inversion is not happening. The image is not closed under inversion. So that is something curious. So of
Sir,
course,
here for
question.
all G means?
Pardon? For all groups. It doesn't matter.
Okay.
See, if you take these two words, if your choice of word is a power word and or a commutator word, doesn't matter. The image is always closed under inversion for every choice of group. Because you replace G inverse in the input.
Yes.
And here as well, you just take the inverse of the commutators again, commutator, but with some symbols permuted. Right?
Okay,
So I guess that is okay. That is independent of the choice of group, but quite often these things are dependent on groups. So there's notion of chirality of groups, and that's what we are going to discuss today. So the question is therefore, what happens in general? So for other words, and what about choice of group? So maybe sometimes choice of groups may have some role play over here. Yeah, so I guess so far things are clear. So that enables me to define the chirality. So the definition, I'll define it through pair. So a pair, group, and word. So that's a group and word is called chiral. And you know what, right? You have already guessed the definition. If if the image is not closed under inversion, and it's a trivial thing, but I think it's good to remark, is that you either say that inverse of the set of the image, or you first invert the word itself in the free group, and for that inverted word, you take the image. Both are same things. So that is not a big deal. And sometimes I will be confusing between this and this. So both are same things anyway. Maybe notationally I could be confusing in that. So I guess things are clear so far. Yeah.
Yes, sir.
Okay. And then this definition allows me to define what a chiral group is. Group G is chiral if there exists a word, some word in some number of variables which participates in the chiral pair. So the GW is a chiral pair. Is chiral. So even if one word exists, you say that your group is chiral. And just to make our language smooth, there's a definition which is I like this word, which is witness of chirality. So an element is called a witness of chirality, and I'm sure you have guessed the definition. Chirality of G if for some word of any choice of D, we have that X is actually in the image of this, but inverse is not there. So in that sense, we say that it's X is witness to chirality. So what you have to do in order to establish that a group is a chiral, meaning it's not chiral, you just ensure that there is no witness. Right? You just ensure that there is no witness, and that will ensure that the group is a chiral, right? So that could be maybe the fourth definition. Not chiral. Okay, so here is the remark. So chiral groups exist. And towards the end of the lecture, I'll try to establish that they are rare, but they do exist. That's the first remark. And an explicit example is here. Well, it's not very explicit because I won't be actually describing it. But some properties of this group I will mention. So this is M11, and those of you who know it, it is one of the sporadic groups, i.e. Matthew group, and this of order some not very large, it's actually quite a small group. So this Matthew group is an example, and let me try to exhibit to you what are the properties of Matthew group which make it chiral group. Okay. As a fact, I will mention, I'm not going to give you construction of Matthew group that comes through certain finite geometries or combinatorial things, but I'll keep a little simpler. So you consider 11 cycle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That is one element, and another element you take 3, 7, 11, 18, and you multiply it with another 4 cycle, which is 4, 10, 5, 6. So I'm not giving you any insight, but some information. So fact is that the group generated by these two inside S11, that group generated, surjects onto M11. Yeah. And that may help you to just see it as a quotient, maybe. Yeah. So what are some properties? So let me point out some properties of M11. Number one, M11 is simple. So it is, I guess, the smallest simple non-abelian group. No, of course, no. Among the sporadics is the smallest, but not among the sporadics is the smallest. Number two, all automorphisms of M11 are inner. And therefore, in fact, because of these two reasons, if you consider the conjugations, G going to odd G, the obvious map, G goes to what INN or INT, inner automorphism, conjugation, and then this is isomorphism. So it's easy to see that Matthew group is isomorphic to its group of automorphisms. And third thing, and maybe this property you might have already seen in some context of some other groups, what is called a real group. So M11 is not a real group. So what is real group? Just to recall. So real group meaning every element is conjugate to its inverse. Okay, so elements for which elements are conjugate to their inverses, they are called real groups. And in fact, for M11, if you take the image of that 11 cycle, that 11 cycle was there, no? So it survives, of course, it has to survive. Yeah, it's one of the generators. So image of 11 cycle in M11 is a non-real element. Non-real element meaning it's not conjugate to its inverse. And once we have all this, we are all set to establish that M11 is chiral. So how? And there I will be actually using Lebovitz's theorem that we saw last time. So I take the following set, following subset of G, of course, it contains identity, and then it contains this conjugacy classes of this 11 cycle. Conjugacy class of this G, 11 cycle. So of course, this is a subset of G. And because all automorphisms are inner, right? That's one of the properties of M11. Since all the automorphisms are inner, what we have is that A is closed under automorphisms of that, and therefore by Lebovitz's theorem, there are, and it's a simple group also. So, and we can see explicitly the two generating set, one of them. So therefore there exists one word such that the image is equal to A, and this image contains G, but it does not contain G inverse, right? Because G is not real. And so it looks like as if M11 is tailor-made for this purpose. There are so many properties which are there in M11. So, yeah.
Amitji, how can we see that A is closed under OT?
Yeah, because all automorphisms are inner, and I am taking conjugacy classes only. That is one of the properties of M11, that all automorphisms are inner.
And the set A is identity and one conjugacy class of
It's
G.
a conjugacy class, yeah.
Yeah,
Okay,
so
So two union of two conjugacy classes, basically.
Yeah.
Okay.
Sir, for a group to be chiral, we need that there exists a word W such that GW is the pair is chiral.
Yes, there exists.
And
Otherwise, yeah, symmetric words you can find plenty.
yeah, but
So
you have
chiral is
given
asymmetry.
Chiral is asymmetry, yeah, opposite of symmetry. Yeah.
but you have said that WG inverse is WG inverse is the you take all the elements in the image and you take its inverse. That is the meaning of WG inverse.
Yeah, which is same as the image being closed under inverses.
Then sir, you have given that means W equals to the commutator and x1 to the power k.
Yeah, so
Those
that is
are-
not chiral. No. So the power map and commutator, they are not chiral. They are symmetric.
They are symmetric, but they are not chiral. So you
Yeah,
said that
therefore they are not
there exists a word W. So we have a word means x1 to the power k and x1
No.
x2.
So there I was mentioning about see, just the that was just a motivating example to start the conversation.
Okay.
Okay, that we are interested in looking for inversion property in the image of word maps. So that
Yeah.
was before definition. That was just to motivate you. Don't quote that for the subsequent discussion.
No, but you said that a group G is chiral if we get any word W such that GW is chiral. Okay,
Yes.
okay, understood. Okay,
And
sorry,
we have found one word. Here's the word
Yeah.
that we have found
There
implicitly.
exists
Thanks to
one
Wolski.
W. There
Yeah,
exists
yeah,
at least
yeah.
one W.
Yeah.
But some
Sorry.
W might satisfy a chirality, but that's not
Yeah.
what we want. We want some
Okay.
random W.
Yeah.
Yes, thank you, sir.
Yeah. But thanks for asking, huh? Okay, so the fact is that M11 is smallest simple chiral group. So the thing that we should focus upon is this. The entire lecture now onward is going to be focused on this question, which is how to detect weaknesses of chirality. Right? That question becomes a sensible question. So here, for example, this G was the witness of chirality. So quite often, say, without even reference to explicit words, we will try to pinpoint some elements and say, hey, you are witness of chirality. And if all the elements refuse to be witness, then we declared that the word is achiral, right? That is the idea. So what properties are there for witnesses of chirality? For that, some quick notation.
Sir, can I ask a question?
Yes, Sumit.
Yeah, so what I had this question a while ago, but since you mentioned this fact, so do we know the smallest group which is chiral?
Yes, I'll come to that also, and that is of order 63.
Okay.
And if time permits, I'll explicitly give that kind of construction. So there's an infinite family of groups, and C3 happens to be the smallest actually in that family, and that is actually the smallest chiral group. I'll come to that.
Thank you.
Okay. So notation is that for two elements in group.
So Amitji, can I ask one just? Hello.
Yes.
So you use the group automorphism are inner simple, then you can use the Lobachevsky. Any simple group satisfies this Lobachevsky result. So if I take AN, most of them are not real, the alternating group, and then their automorphism is also inner. So the same recipe will work, right? Or no?
There might be some issues.
Because I can take A, let's say A maybe 10. No, 10 is I think.
For A5, I think all automorphisms are inner, but not for A6. But let's say A5 only.
A6 also, like few ANs are real also, so I remove those.
Yeah.
Like I think there are.
Yeah.
So if those are, so then I can able to find out a G which is not conjugate to its inverse, and automorphisms are inner, and also it's a simple group. Therefore, Lobachevsky's will be applied, and then it seems that will be chiral.
Yeah, it should not be, but at the moment I don't know how to argue. So maybe in the tutorial we can take that, Sushil, since you are the tutorial in charge also. Thank you for that.
Okay.
Okay, so the notation is simple. Well, you take any two elements and you take homomorphism. Or automorphism. Well, so what I want to say is that if there are two elements such that there is an automorphism which takes x to y, then we will say x and y are automorphic. And if there is a homomorphism, we will say they are homomorphic. That's all. So this is notation. So they are homomorphic automorphic if phi exists such that phi x is y. That's this is not a big deal, but it improves the language later on. So two elements are automorphic or homomorphic if there is a homomorphism or automorphism which takes one to another. And because that's where our first observation starts about witnesses. So we have to identify witnesses. So observation is that if x and x inverse, they are homomorphic, then x cannot be a witness to chirality. Not difficult. Maybe all such things we can take up in the tutorial for details. Yeah. So if x is homomorphic to its inverse, then it is not allowed to be a witness. And that's how we start identifying many witnesses. So here is very powerful statement. It's a lemma which is 100-year-old, but still quite useful. So here I am saying, here we are now playing with words. The juggler is required. So you take FD, and you know what it is. Free group on all these free generators, x1, x2, xt. You take W, the word in this, and you take an automorphism of FD. And then the statement is, I hope I don't run into controversy on that, because tutorial had some such thing, but not quite the same thing. The statement is then the image of W and image of sigma W, they are equal for every group. Okay, so here I am not talking about embedding of one free group in the other. No, that was the case in the tutorial in last lecture where we had that discussion. Here I am talking about automorphisms of FD. Okay, and under automorphisms of FD, what is being said is that the word images for all groups remain the same. And I'll sketch the idea behind such a thing. So proof is, we explicitly try to understand automorphisms of free group. So this is generated by following transformations. Transformations of symbols, maybe, if you allow me to say that. So what are those? First, First is switching. Switching meaning, you know what it is, right? Xi, Xj. You just swap them. And that is an automorphism of free group. Other is cyclic permutation. Well, cyclic permutation is kind of repeated switching, but it deserves a special mention. X1 goes to X2, and like that, goes to some XR and comes back, right? And third one is you can swap Xi with its inverse. That's also an automorphism of free group. Okay, I'm not asking you to swap a word with its inverse, but a free generator with its inverse. And these operations look very much like matrix operations, you see? Famous row or column operations. So here, replace Xi by, or you replace Xi by Xi Xj, or I not equal to J. So you consider these transformations, and here's a theorem. It is Nielsen's theorem. Uh, 1921. So we are celebrating 100 years of this result, and this was this is not this paper is not found in Math Scienat, but in the Zentra Graphics there. And the journal, the spelling is somewhat different, but pronunciation is similar to some other journal. Math script or something. It's Finnish. It's actually not in English. It's in Finnish language. Okay. So now the thing is, since these transformations, that's a Nielsen theorem. Oh, what did I say? Generated by that, right? So since these transformations preserve word images, right? I guess that is clear, that those points are clear.
So
Because
Nielsen's theorem is this description of the automorphism group, is it?
yes, generating set of the automorphism of free groups is Nielsen's theorem.
Okay.
The statement is generated by, right?
Okay.
That is Nielsen's theorem. Yeah, and we can observe that in each of these cases, the word images are not going to suffer at all. Yeah, so that is the first thing, and that gives us a motivation that perhaps we should focus on words of special type, words of specific type, right? And for that, let me write lemma, which is not difficult. Perhaps in the tutorial also we can carry it out. So lemma is that each word, you take any word, then it is automorphic to a word of type let me say one of the symbols x1, some power, so it's the power word times commutator. for some C in FD derived subgroup. So each word is automorphic to some group, some word of specific type, and because of Nielsen theorem, because of the observation above, this one, we can focus on words of this type. So words of this type are there in our consideration now onward. Okay, so in fact, using all that, I can derive the following. Maybe I'll skip the details. So what's the consequence of all such things?
Sir, can I ask one question?
Yeah.
Yeah, it seems like then for abelian groups would always be a chiral, right?
Yeah. Yeah. I see. Regarding that only, the consequence that I'm going to mention may have some answer to your question. Just let me just finish this. Yeah.
Okay, thank you.
Let me just finish. Yeah. So I'm just skipping some details, but the consequence is interesting. So I take a group. Let G be a group, and E be its exponent. And if for every k which divides E, so you take the exponent, you consider all the divisors of E. Every element of what? You take gth power, kth powers, and you take the commutator. Okay, minus, you consider this, right? So if every element of the kth powers minus this is not a witness of chirality, then the conclusion is then that's all. Then don't find witness anywhere else and declare that then G is a chiral. So if Sumit, group happens to be abelian, then what are you inclined to conclude from this? Because in that case, this quantity is going to be just empty set, right?
Yes, that's exactly what I had in mind.
Yeah. So you don't have to worry in that case, because there is no hypothesis as such. So G is a chiral, right? So this is again not very difficult thing to prove using whatever I mentioned, Nielsen transformation and all that.
For abelian group, the word image is always a subgroup, na? So it's closed under
Yes,
inverses.
it is following from the
Yeah, anyway, yeah, right. It doesn't prove so in any case, yeah. Okay. So shall we move ahead? Yeah. Yeah, I'm skipping the proof as such. Yeah, it's not much difficult. Okay, so let me come to the other. Here is the other interesting part, and that's how you actually, whatever examples of non-chiral groups we know. So whatever examples of chiral groups we know, a huge family is due to following discussion. So this is chirality in semi-direct products. So semi-direct products, and as everyone would recall, look something like this, right? So you have two groups and certain action, and this semi-direct product. I'll maybe quickly recall it, yeah, so that everyone is with us. So H acts on N. So you have two groups, and one of them is acting on the other, and group law is being considered on the pairs N comma H, and the way group law happens is, just to recall you, N1H1 times N2H2. There is some small twist, not the direct component wise, but it is N1 phi, the action, phi H1 N2, and then H1 H2. So when you start with two groups and an action like that, and form a group with this group law, then this is semi-direct product, and we are interested in understanding chirality in semi-direct products. Yeah, so it's a fact that it's a basic fact in, I think, first course in group theory itself, that N sits normally as normal subgroup inside a semi-direct product. Okay. Now a couple of things I'll just mention as tutorial exercises maybe. So first is that this is easy. Still, if N is abelian, then there exists an automorphism. Maybe this phi is not to be confused with that phi. So maybe I can just change this notation. I don't know what. Maybe psi. Yeah. So then there exists automorphism of this semi-direct product such that it acts as inversion on N and identity on H. So basically you define map like this and show that it is automorphism. Okay, so there is an automorphism which inverts N but keeps H intact. And yeah, second thing is that if you are given a semi-direct product and a word, then if H is in H and H is coming as image by plugging in certain variable, plugging in certain elements of G, then you can obtain this H by plugging in elements of H also. That's all. Yeah. So these are easy exercises. And what's the consequence? I'll not say in detail, but just so two consequences I'm mentioning for semi-direct products. First is that if you have a semi-direct product in which the participant H, the H is a chiral, then elements of H. So H has decided not to have any witness for itself. Then after taking semi-direct product with an abelian group, so no, this is not abelian required here. So it's any n. So then in any semi-direct product like this, elements of H will not be witness for. They cannot witness chirality in G also. Okay, and main thing is, if further n is abelian, so if you have semi-direct product with an abelian, then so all thing is about identifying witnesses. Then witnesses of chirality of G, they cannot be automorphic to elements in N union H. Okay. So if an abelian and H a chiral. So if you take abelian a chiral like that, then neither N nor H, those elements, they don't allow their elements to be witnesses, and of course up to automorphic also. So anything which is automorphic is not going to be there.
So it is cannot be
Cannot be.
automorphic or
Cannot be.
Cannot
Cannot be. Yeah. Thank you. So any correction should come in red. Okay. Fine. So the idea is that we should be able to pinpoint the witnesses. That's the basic idea of the discussion. Okay. So maybe I should say this. Yeah. Yeah. Maybe I'll just state it as a theorem only, and then that will motivate. So statement is there are only, so this is for small groups, there are only two achiral groups. Not achiral, sorry, chiral. Order. And their orders are 63 and 80. Okay. So what goes into such things? The point is that in order to declare that yeah, in order to find chirality, you have to really visit lot of words, right? You have to check with lot of words, because even if you are simplifying your situation by going into this, but your group may be bad, because there might be so many words which are coming from the commutator part, which are coming from FD derived subgroup, right? And quite often those are the words which create a lot of problem. So it's although simplified, but not that simplified a situation. Okay, so what goes into this? Maybe I should just say it as a proof. So there are two parts of the proof. So one is to show that these are chiral, and then to show that there is none which is chiral. So one is more computational part than other. Okay, so the proof is there in this lemma, and this is some very nice observation by this William Koke. So you consider this. So all this CP, CQ, they are all cyclic groups. So I'm saying that this zeta p is the generator of it, and it goes, some action is happening. So phi zeta p. So these CP, CQ, they are cyclic. With generators. And what does phi do? Phi, that is no, sorry, phi zeta p acting on zeta q, that takes it to some power, right? So I'm just writing that power as phi. Okay, so phi is defined like this. And yeah, and if the following things hold, if this thing zeta p going to, sorry, zeta q going to zeta q to the power phi, this thing has order p in odd CQ. So if all these conditions hold for some, because this will restrict choices of P and Q. And other condition is pi minus 1Q GCD and phi plus 1Q GCD, both are 1. Okay, if that is happening, if some condition is happening regarding some cyclic groups and their automorphisms, then they construct some witness of chirality. So then for every R, I think, yeah, then for every R, what we have is CQ semi-direct product C PR. So it's not, it's P times R, not P to the power R. That is chiral. With respect to the word, they also give a word. I'll just write that word. W is x1 to the power p, x1, x2, and x1 inverse x2 phi. Phi is that integer. Phi is an integer which was constructing this automorphism. And and this action is whatever is the natural thing in the context. So action is coming from raising power by phi action, that action. Okay. So what you can do is you can use this to construct certain chiral groups, and using this you can actually construct, you can establish the chirality of these two groups, 63 and 80. But then you also have to ignore many of them, right? And for that, one has to establish a certain kind of a systematic way of computation. And what these people say, Neumann type algorithms. So that is second ingredient in the proof, and which they say, because you also have to prove that other things for other groups, chirality is not there. So they constructed example of saying that direct product like this, and the computation they are calling it meaning you systematically describe the process through which you are going to check all the words and all the witnesses. The point is that there are so many words, even after considering the words of the type, say x1 to the power k, where k is the divisor of exponent. So x1 to the power k times commutator word, or a word which is coming from the commutator subgroup. So there are so many. So can you describe the whole thing as a kind of finite problem? And that is the meaning of some Neumann type algorithm. So this indeed turns out to be a finite problem, although we are dealing with free group. And for that, so this is inspired by a work of, there were many Neumanns. This is, I think, the senior most. In fact, it was the first paper, at least in my sense, it is the first paper of Neumann. But that was in some other context. But these people are just drawing the inspiration from that. So here is a lemma, which is quite useful and not difficult to understand and not difficult to prove. So, so I take this group which is degenerated, meaning generated by D elements. Okay, so G is a finite degenerated group, and the statement is then G is chiral if and only if you can find word in D variables such that GW is chiral. So what's the crucial part here? The crucial part is this one. In D variables. D is the crucial part. You don't have to go beyond D. And in fact, just to focus on FD, the word in D many symbols, and that quite restricts the scope of our search. Yeah. And the way the proof happens is interesting. Okay, so let me actually prove it as much as I can. Because the idea is very simple. So the statement should be clear.
Sir,
Yeah.
don't you have to say that D is strictly greater than 1?
Yeah, well, otherwise you are having cyclic groups. Yeah. So there the problem is not interesting, right?
Yes,
you
yes.
are, yeah.
I mean, it's
Okay.
trivial, but I just
Okay. You want me to say that also? Yeah, sure. Yeah. Okay. So proof is what you do is you do it the crude way. So you just strictly write down. You just write down what are you doing? You are enumerating G, right? You are enumerating your group, and each AI. So since the group is generated by these G1, G2, GD, so I can write each AI as a combination of these, meaning as a word in these, right? So that means then there exists a word. There exists UI in FD such the combination meaning what? So that particular combination comes as a word. So then there exists UI in FD such that UI of, when you evaluate it on generating set, what you get is element number I of the group. Okay. So you have obtained therefore many words like this. Okay. Now what you do? You take any word of any number of variables. Fk. K is anything. Be any word. K variables. Okay. And then what do? I in that word V, which is there in K variables, I substitute things from the word UIs. And this I'm just doing randomly with all possibilities. I'm just substituting. It's like UI1, UI2, like that, UIK. So after substituting, what I get is actually a word, right? So see, so when I say V is in FK, and then I'm treating, I'm evaluating this K variable word, K variable word on FDK. So K many copies of FD, and I'm getting a word in D many variables, right? So this is a word in D many variables, this one. So I evaluate it on D copies of G, and what I get is on the other side, on the other hand, it is also the substitution can happen either at the level of word, either at the level of free group, or it can also happen at the level of the group G, right? So if it happens at the level of group G, then it is simply lying in the image of this. This is not difficult. This is just maybe the notation might look a bit cumbersome, but this is just substitution that I'm doing. I'm substituting one word in the other. Yeah. So now what we can do is we can vary these UIs. We vary UIR inside all possible things, inside U1, U2, all those words which were there, U1, U2, UG. Those words which were describing, those which were enumerating elements of G. So what do we get? From that, we'll actually get that I should say, if you vary this, it's a free group, and not in terms of this. So certain union, right? Also all possibilities, maybe all possibilities. Yeah. UI1, UI2, UIK, GD. So this is all possibilities of UIR. So I guess you understand this I'm varying over all possibilities where UIRs are varying inside the choice of words that we had to start with, right? So so this is contained in VGK, but it's not actually difficult to argue because of the generation thing, because of the generation, that this is actually equal. This is actually equal. Okay, because every element here would because every element, when you substitute, when you have V and you have some element, say X, not X1, maybe some V, say elements of GI, so R1, R2, R3, or all those elements are expressible like UI something, right? So every element here belongs to something of this form. So this is not difficult, you just have to convince yourself. Maybe in the tutorial we can take this equality. The point is that your choice of words UIs is like that it enumerates everything. So anything on RHS will also belong to LHS, although this containment is easy, but the equality also holds. Yeah. So now I can immediately pick the, suppose chirality is not there, right? So if V is not chiral, V was arbitrary word of K length, K generator. So if V is not chiral, then some element of the form, then some element in the, so if it's not chiral, then some element here witnesses the chirality. Therefore, it belongs to some element of the union. Okay, so then some element in a suitable image of in, maybe I should, in some one of the image V U1 or UI1, UI2, UIK witnesses chirality. And if you look at this, what it is just substituting, right? All these are words in D length. So eventually what this is actually in FD, right? So this is an element of FD when you substitute like this. So therefore, given any arbitrary element, given any arbitrary word of arbitrary number of variables, I have constructed a word of length D, word in D many generators whose image witnesses chirality, some element in whose image witnesses chirality. And therefore, for the entire discussion on chirality, we can focus only to the D variables. That is the message. And we can actually use it to construct this algorithm. So one may use this idea to systematically look for fitnesses in finite time actually. And to do that, I am just saying in short words using actually there is a concept of variety of words and all that. So using some such thing, but in the simple language, using calligraph of word maps in fixed number, which is D variables on G. So what is this calligraph of what? What is this? So you can actually construct, you can take the set of word maps in a fixed number of variables in a group G, and it actually, so if all the word maps you denote by WG, so you just see them as maps over that particular group, not as a word in a free group. You see it as a map for a particular group. Okay, so WG is a collection of all word maps in D variables, and it comes with a group structure. It has of pointwise multiplication. And identity of this group is, identity of WG is called law on G. So law meaning a word whose image is trivial. So it has a group structure of pointwise multiplication with, you take any law word and that is the identity. And in fact, you can show, and it's not difficult in fact. Yeah, since I'm just showing the finite process. In fact, WG injects inside D copies of G. How? So you take Xi and you go to, we have fixed the generators, right? G1, G2. So you take it and you take one like that. You can go to Gi, 1, and so on. So this is ith. Therefore, you will eventually end up visiting everything because this is finite. So that's the basic idea. So that is what is called a Neumann type of algorithm. So here you have put your words on for a particular choice of group in a finite thing, and then because of this observation, D is fixed. D has been fixed, and that allows you to accomplish establishing chirality in finite time using an algorithm. Yeah. So it does not give you any analytic proof, but it says that it's a finite process. Yeah. And I would just end up giving some remark, and in the end, maybe I'll also mention at least one open problem. So remark is that one can also interpret asymmetry in images or in word maps in some other ways. So maybe I would end with a couple of remarks. So first is that you may actually fix not inversion this time, but any other anti-automorphism of a free group. Anti-automorphism of free group, and similar kind of thing you can do and define a word to be gamma chiral, right, on a group G, if you know what I am going to say, right? If image of W is not equal to image of gamma W, right, for this G. And then you can and ask similar questions. And you can try to find out asymmetry at other level also, which is at the level of fibers of word images. And that is somewhat not very well studied. So but there are lots of open problems, and asymmetry phenomena can also be studied with respect to fibers, and I'll explain what those are. Oh, bad handwriting. Fibers as follows. So what you do is you fix a, or not fix, take a word and also take an element in the group, and what is fiber? Fiber is inverse image, right? So W inverse A is G1, G2. We have the variables Gd such that all of them evaluate to fiber may be empty also, right? If A is not in the word image, then fiber will be empty. So this is fiber.
So is this like you are using homomorphism instead of automorphism?
No, there is no homomorphism here. So W are words, na?
Okay.
This is just as a map,
No,
right?
did not make a homomorphism. Yeah.
It is just a set theoretic map, inverse of set theoretic map.
Okay.
Yeah. And in fact, a lot of what is called probabilistic group theory is just about understanding fibers. But here is another question, not in the probabilistic group theory, but in general, which is coming up. Maybe it has solutions in what is called probabilistic group theory. So I just end with this definition and the question. So definition is that for a given anti-automorphism, and yeah, so the group G is called weakly gamma chiral. Weak if you consider fiber sizes, so if there exists A in G and a word such that W inverse A you consider, and you consider gamma W inverse A, you consider these two fibers. So these are of different cardinality. So interestingly, question is asked at the level of fibers here. So if with respect to anti-automorphisms, these fibers turn out to be of different cardinality, and the it's a tutorial question that will come up. So you can solve it in the tutorial. So statement is, well, there is a reason that it's being called weakly gamma chiral, right? So what's the reason? Reason is that, and tutorial will clarify this. So gamma is G chiral, then no, not gamma is G chiral, G is gamma chiral, right? G is gamma chiral implies G is weakly gamma chiral. And I'll just end with this question, which is actually very much open and may lead to, its answer may lead to very interesting connections between images and fibers, and this is not known at all. And question is the famous question which anyone can ask after any lecture, even if you were sleeping. The famous question, is the converse true? That's the question. We don't know the answer. So yeah, with this I stop saying things. Thank you.
Thank you, Amit.
Yeah. So do we have
There are any
questions?
questions? Yeah. Wait.
Yes, sir, I have a question.
Yeah.
So when you define this another version of chirality using automorphisms, so is it clear that it's actually a more general thing, like maybe this is same as
Yeah, you are absolutely correct. You're absolutely correct. So all those are open questions.
okay.
Yeah. And yeah, there is something in the chat.
That's another famous question you can always ask.
I thought that